So no fancy fun little domino type videos for this one. However, there is going to be a link posted on D2L and probably in the description of this video that links to another YouTube video that I like that explains functions in terms of machines, which is the way that I like to think about them. If any of you ever take any higher mathematics classes with me, like topology especially, or even complex analysis or reals or algebra, I will talk a lot about how functions are dynamic. And the set theoretic definition we're about to look at makes them look like static objects, but it's better to think of them as dynamic, as things happening, where you input and they output something. But like I said, if you take one of those classes with me or do an S-Tech with me or something, we will talk a lot about that because as a topologist, we do a lot of stuff with functions. Okay, at any rate, let's just jump right into it. We typically think of functions in college algebra in a couple different ways. One way that we might think of a function is just as a graph, right? When you hear the word function, you think of, oh, well, this is just a graph of something. But I want you to think about what that means, all right? When you say, oh, a function, it just has a graph like that. Think about what you're saying. Implicit in that is there is an x-axis and there is a y-axis, and that means something. Those aren't just arbitrary concepts. And then we have this thing. What is this thing? Well, it's a graph, right? But what does it mean? We represent it with something like, oh, this is y equals f of x. That's saying something very important. Okay? It's saying something very, very important. It's saying that this wavy line, the points on that wavy line, what are they? Well, they correspond to something along the x-axis and something along the y-axis, and a rule that determines which y value you pick, given a certain x value. Okay, and we're going to generalize all this stuff in a more mathematical framework. Another way you think of functions when you're very first learning about them is something like this. You might have x and then f of x and a table. You know, -1, 0, 1, and f of x could be, I don't know, 1, 0, 1. So this is kind of leaning towards what a function is. Another way that we'll see later on, when we'll formalize it, is we have these little, I had a friend in graduate school who called these bean diagrams. You could give a function by saying, well, I'm going to send 1 to 3 and 2 to 1, and that's all I'm going to do. So these are all different ways that we think about functions. And the most important way, or important's the wrong word, but for me, the most morally correct way would be something like this. So I have a box. Oh, I messed up my picture. Let me start over on that. Okay. I have something up here that looks weird. And I have a box, and that thing that looks weird is a little tube top device on the top of the box. And then I have another tube top device to the left of the box, so to the right side of the box, and I have a little handle. And this is my function machine. It takes inputs, which we typically think of x's, but we're going to get away from that. Takes x's, go inside, and I turn the handle, crank, 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 and it spits out a y value. But the important thing is that y value is entirely determined by what that x value is. You learned in college algebra or before somewhere else, the set of all these inputs is the domain, the set of all these outputs is the range, and for each input you can get, or there must be, a unique output, and that's what makes it a function. So these are all the different ways that we think about functions. We're going to formalize that now mathematically over the course of this section. Okay, so here is a function. A function from a set A to a set B is a rule that associates with each x from the element A exactly one element of the set B. That's what makes it a function, that each x element from A is associated with exactly one element of the set B. Notice that it cannot be more than one, but it also can't be nothing. Okay, x has to be associated with something out of B, but it can only be associated with one thing. And then a function from A to B is also called a mapping from A to B. But be a little bit careful when you, if you're reading other papers or books or anything. Sometimes mapping specifically refers to what are called continuous functions, especially in the context of topology or real analysis. Okay, now, notation. This is the notation we use to denote a function. F colon A arrow B. And the LaTeX to get this thing right here is /right arrow. So the way we read this is F is a function from A to B. F is a function from A to B. Now, we call A the domain of the function F, and write A equals domain of F. And this might be something new. B is called the codomain, not the range. It's the codomain of the function f. And we write B equals the codomain of f. So if A, little a, is an element of A, then the element of B associated with it is f of A, just like you would expect. Now this is an important bit of terminology, and as a matter of fact, I'm going to circle the things that may be new, like codomain, image. All right, you need to be familiar with this. F of A is the image of A under F. And if F of A equals B, with B and B, A is the pre-image of B under F. We're going to do some examples to kind of make this a little bit more intuitive in just a second. But here's kind of the key takeaway here to distinguish these two things. If I start out with something in A, and then I apply the mapping F, I get something in B over here. Whoops. I get something in B. Okay? I have an image. If I'm going from A to B, I have an image. However, if I start out with something in B, and I want to find out what particular A goes to it, then I have a pre-image. That is something that happens before I apply F. So here are some examples. All right, so we're going to take two functions. First one is going to be f from r to r. It's going to be x squared minus 5x for all r and r. Okay, so I have a function from the real numbers to the real numbers given by this definition. And I'm also going to define a function g. Now this function has a different domain. This one starts in the integers and goes to the integers. All right? I'm going to define this one the same way, m squared minus 5m. That is, it's going to have the same, I do the same thing to domain elements to get codomain elements. Okay, so let's see some examples. Now some of these I think I'll have room to do on this slide. Some of them I'll have to do a new one. Number one, determine f of negative 3 and f of root 8. You guys know how to do this, so I'm going to go through this kind of quickly. F of negative 3 is equal to, well, what do? I look at the definition of the function right here. Everywhere there's an x, I plug in a negative 3. Negative 3 squared minus 5 times negative 3. That's going to give me 9 plus 15 equals 24. So that's what f of negative 3 is. I'm going to write it up here at the top so that I can erase. Okay. Let's do the other one. So I'm going to go ahead and erase all of this. Why won't you erase? There we go. let's do the other one. F of root 8 is root 8 squared minus 5 root 8. So we're going to get 8 minus, I know that we could simplify this, but I'm not going to bother. 5 square roots of 8. So f of root 8 is 8 minus 5 square roots of 8. Okay. Let's go on to the next one. Next one, now we're dealing with the g function, g of 2 and g of negative 2. G of 2 is equal to 2 squared minus 5 times 2. It's going to be 4 minus 10, which is negative 6. So g of negative 2, g of positive 2 is equal to negative 6. And I'll just do the other calculation up here. G of negative 2 is negative 2 squared minus 5 times negative 2, or we're going to get 4 plus 10, which is 14. Okay? Like I said, you all know how to do this. The reason we're doing this is, well, a couple things. One is to make sure you remember how to do this, to make sure that you're not going to be sloppy with your parentheses in places like this. But I'm going to make a distinction about what functions are. Okay, even though they have similar definitions right here, these are not going to be the same functions because they have different domains and codomains. We'll get into that in a second. For now, let's look at maybe number 3 and number 4 from this problem. So describe the set of all preimages of 6 for the function f. Okay, all the preimages of 6 for the function f. So I'm going to go to a different slide to do this. All right, so we have a function defined from R to R, defined by f of x is x squared minus 5x. Find all the preimages of 6. So what is it we're looking for? We want all x a real number so that f of x is equal to 6. That's what we're looking for. All the real numbers x such that f of x equals 6. So by the definition of the function, we're looking for everything like that. In other words, we're trying to solve x squared minus 5x minus 6 equals 0. And it doesn't take too much to factor this out, and you'll get that x is going to have to be equal to positive 6, or x is going to be equal to negative 1. Okay? So those are all the preimages. We could even say that the set of preimages of 6, or the set that contains the preimages of 6, is equal to 6 and negative 1. Okay, now, a little side note, if we did the same thing with g from z to z, where g of m is equal to m squared minus 5m, we want to find preimages of 6, well, the exact same thing would happen. We would be solving g of m equals 6, go through the exact same process, and see that m is going to be equal to negative 1, or m is going to be equal to 6. Yeah, so keep that in mind as we proceed. Okay, what if we try to do the same thing, but instead of preimages of, I think 6, we try to find preimages of 2. Well, try to do the same thing. We're trying to solve x, okay. Let me not jump ahead that far. We're trying to find all x in R so that f of x is equal to 2. That is, x squared minus 5x equals 2. X squared minus 5x minus 2 equals 0. This doesn't factor at all. As a matter of fact, you have to use a quadratic formula to solve it, and you'll get that the solutions are x equals 5 plus root 33 over 2, and x equals 5 minus root 33 over 2. Those are the two solutions to that quadratic equation. So those are the two pre-images of 2 under this function. That is, if I plug in either one of these two real numbers into this function, the output is going to be 2. What happens if we try that over here? Okay, here my function is defined from z to z. That is, the only valid inputs are integers, and the only valid outputs have to be integers. Okay, I have to end up with an integer. So if I'm looking for all m in z such that g of m equals 2, if I try to play the same kind of game, m squared minus 5m equals 2, I'm going to get that m has to be of the form 5 plus or minus root 33 over 2. This is not, okay, let me say it this way. Once I get to the end, this is not an integer. So what does that mean? It means 2 has no preimage under G. And this is the distinction I wanted to make. Okay? Even though these two functions are defined similarly, okay, you square something and then you subtract 5 times that something for both of these. The fact that they have different domains and ranges, domains and codomains, see, I slipped up and said range. Domains and codomains can change things, because this function does have preimages of 2, this function does not. That's an important point, not just a little nitpicky detail. All right, so here's another way to define a function, set theoretically. A function from a to b is defined as a subset of a cross b that satisfies the following condition. Now, before I go into that following condition, let me talk about what a cross b is if you haven't had Calculus 3. You know, if I were in class, I would talk to you and ask you who's had it, but I can't do that. Okay, so let's see what this is. If a and b are sets, we define the Cartesian product, sometimes called the cross product, a cross b. This is the set of, it's just a set of all ordered pairs. It's a set of all ordered pairs AB such that A is an element of A and B, not capital B, of course, and B is an element of B. And that's all that is. Okay, that's all that is. When we talk about elements of the plane, the XY plane, we're talking about R cross R, or R squared. Okay, so all ordered pairs where the two elements, the first element and the second element both come from R. Ordinarily, we would spend more time on this, but you'll get into the details when you take your other upper level math classes. So, but we need that to do the set theoretic definition of a function. So a function from A to B is a subset of the cross product or the Cartesian product A times B that satisfies the following conditions. And I lost my definition. Let me see if I can fix that. And magically it appears. Okay. So function from A to B is a subset of A cross B that satisfies the following condition. For every element of A, that is every element in the domain, there is a unique element in the codomain such that the ordered pair A comma B is an element of F. Now that might sound a little weird. What do I mean by an element of F? I mean we're able to now think of the function as a graph. When I say A comma B is an element of F, I mean that this is an element on the graph where capital A is the horizontal axis, capital B is the vertical axis, and I have an ordered pair AB as an element of F, an element of a function. So now we don't have to just use x's and y's. We could have arbitrary sets, and we could represent the horizontal axis with an A, the vertical axis with a B, and then AB gives us the ordered pair AB, and now that is an element of my function f. As long as it passes the vertical line test, basically, as long as for each element of A, there is a unique element of B. Yeah. Okay, some more terminology. Let f be a function from A to B. This set, the set of all f of x's, where x is an A, this is the range. The range is the set of all outputs. The range is the set of all valid outputs. So it's the set of all f of x's such that x is an A. And it might be a good idea to keep in your head. You don't have to write this out, but these f of x's are all elements of B. Okay? Set of all f of x's in B such that x is an element of A. That is the range. And the range is sometimes called the image of the entire function. A second ago we talked about images of elements. The range is the same thing as the image of the function, or the image of A under F. Now, in just a second, I'm gonna have some more exposition words pop up to explain something. But let me just draw some pictures that can maybe illustrate this a little bit. Suppose I have over here a set A, and I'm drawing this larger on purpose, a set B, and I have a function between the two of them, f. And f is a legitimate function. So every element of A gets mapped to a unique element, f of A, inside of my codomain. Okay? What is the range? The range is a subset of the domain. Okay? So this is the range of f. In other words, the range is every single element that I pick in A, I pick all of them, and I apply the function f, and then I get this. That's what the range is. So it's almost like a copy of A inside of B, okay? Subject to what the function actually does. Okay, but you can think of it as like a copy of A living inside of B, where I've applied this function to it. That's the difference between the range and the codomain. And in generally speaking, the range, actually this is true in general. There's a more particular case we'll see in a second. The range of f is a subset of the codomain of f. And under some circumstances that we'll see, I think in section 6.2 or 6.3, they're going to be equal. But generally speaking, the range is always going to be a subset of f. Okay. Now, all of this picture stuff is going to vanish because I need the room to put some more words up. So pause the video if you want to write this down. Because now it's gone. Okay, now we can also describe the range like this. The range of f is equal to every y in B, such that y is equal to f of x for some x in A. Okay, it's every element of my codomain, such that y is equal to f of x, where x is something out of my domain. And like I said before, we always have that the range is a subset of the codomain, but we do not have that the range is equal to the codomain. And this would be a nice little thing to think about in terms of functions from the real numbers to the real numbers. You know, can you think of some where the range is going to be equal to the codomain? Can you think of cases when it's not? And maybe you can figure out, you know, what makes that distinction before we get to it, if, you know, officially get to it in class. Now, the ones that you're most familiar with are what are called real functions, or sometimes real valued functions. And this is a function whose codomain and domain are subsets of the real numbers R. Most or even all of the functions in calculus are real functions, and we usually use a formula or a graph without talking about domain or codomain or range or things like that. You know, in calculus, we just assume that the domain of every real function is R, and the codomain is R. So for example, this function right here, f of x is equal to x divided by x minus 2. We assume that the domain is real numbers, not equal to 2. Okay? Remember what I was saying about a real valued function? Subsets of the real numbers. So the domain are all real numbers not equal to 2, and the codomain is R. Okay, and then the range would be all of the outputs, which would be a subset of R. Now, it would be very, very useful and a nice exercise for you to go back and review things you know about domains of real valued functions, okay, and when it's not going to be all the real numbers. So some examples to think about would be functions involving square roots. You know, what does having a square root do to the domain of the function? Obviously, you can't take the square root of a negative number. Functions involving, you know, logs of any base, okay? You know, what are you not allowed to put in there, right? You can't take the log of negative numbers, you can't take the log of 0. Obviously, fractions, you can't divide by 0, but things like that. Just make sure you're familiar with how that works. And maybe you could do some examples like, you know, work on your own and find some examples like find the domain of things like square root of 2x plus 4. Find the domain of the natural log of the square root of 2x. Or find the domain of, this is, I don't know, I'm not too crazy, x divided by the natural log of x plus 1. You know, things like that. This is stuff you've done in college algebra or pre-calculus, whatever class you took. But, you know, make sure you know how to do stuff like that. Okay, here's something else that you're pretty familiar with. Let A be the set 1, 2, 3, B be the set AB. I'm going to define a function called capital F from A to B by specifying that f of 1 is A, f of 2 is A, and f of 3 is B. Now, for nice, when we have sets that are finite and that are like small cardinality finite, we can use something called an arrow diagram to represent them, and that's all that it is. It's what I called a bean diagram before. You have your set A with the points inside there, you set B with the points inside there, and then your function going from A to B. And this is nice because it kind of illustrates something for me. The rule in a function is that every element of A is associated with a unique element of B. So the element 1 is only associated with A. The element 2 is only associated with A. And that's fine. I can have two different elements of my domain going to the same codomain element. No issues whatsoever. What can't happen would be if I wanted to say something like, okay, I want 1 to go to A, and I also want 1 to go to B. That's not allowed. That would not be a function anymore, because I don't have 1 associated with a unique element. One way to think about it is like, you know, if you're shooting targets, unless you're Hawkeye or something, you're only going to shoot at one target at a time. I can only shoot from 1 to A. However, I can have two different people shooting at the same target. You know, there's nothing wrong with that. Okay. So here's an example. Let A be the set containing A, B, C, and D. B be the set A, B, C. C the set S, T, U, V. And in all these exercises, you just draw an arrow diagram to present your function when it's appropriate. So can you create a function from A to C whose range is the entire set C, or explain why not? Okay. So I'm actually not going to do these this time. If you'll notice at the upper left, this is an exercise, and I'm actually going to assign it to you. However, I'm going to give you some pointers. Okay. So you're just doing arrow diagrams. So if you were drawing this, you would have A, you would have C, a function going between them, and then you have 4 points for the elements. Oh, crap. A, B, C, and D. There we go. And you're going to have 4 points for C, S, T, U, V. And is it possible to have a function whose range is the set C? So in order for the range to be the entire set C, each one of these elements over here has to be hit by an arrow coming from A. Okay? And there obviously is possible to do that. And there's multiple ways to do it. But that's what you're trying to figure out. Is there a way to draw arrows coming from A into C where each one of these guys gets hit? And that means the range would be the entire set. Now for this example, can you do it where I have A, B, C, and D, and now I want the range to only be U and V. So your picture is going to look something like this. I'm going to use a different color because I'm getting tired of the red and the blue. So I have A and C and a function between them, F, A, B, C, D, S, T, U, V. I didn't mean to get sing-songy there, but it's fun. It's late. Okay. If I want the range to only be U and V, that means I have to have arrows coming from these elements that only hit U and V. Is that possible? Think about that one. Try to do that one. Now, similarly, can I make a function from B to C whose range is all of C? So try to do the same thing. Draw the two sets, but I only have 3 elements to work with and 4 elements to work with over here. And see how that changes things from part A of this problem. And part D, do the same thing, or try to do the same thing from A to C, where the range is W, or explain why you can't do that. And now here's something that's interesting. Is it possible to make a function from A to C such that for all elements of A, if they are not equal, then the images of them are also not equal? So this one you may need to play with a little bit. Okay? This one you may need to play with a little bit. And think about what it's asking. So let me kind of illustrate something. I'm going to use yellow. Let's use yellow. Why not? A, B, C, and D. S, T, U, and V. So what is this condition asking about? It's saying, is it possible to make a single function? I'm not saying find all the possible ways to do this, but can you take a single function so that whenever I have 2 different elements over here, their images are going to be 2 different elements over here? Okay, that is, A and B are 2 different elements, and if I send A to S and B to V, then their images are also different. You know, I have A is not equal to B, and f of A is not equal to f of B, because S is not equal to V. Okay? That is, f of A is equal to S, f of B is equal to V. And, you know, these are not equal elements over here. So is it possible to finish this? Can you tell me where C has to go and D has to go so that it's going to be true for all of them? And I think it's kind of obvious what that works. And the last thing I want you to think about is this. Is it possible to make a function from A to this 3-element set where that same condition holds? So try to work that out. This is a nice thing to think about, and it kind of is anticipating what we're doing in section 6.2, or maybe 6.3, I forget where we cover it, but something that's important that we're going to cover about injective and surjective functions and things that are really important in, you know, a lot of your upper level math classes, but particularly in abstract algebra. Okay, think about that. This is the last thing I have to show you all. Email me for questions. Email me if you want to get together and do a video chat. Yeah, have a good day. Stay safe. I hope you and your families are all doing well. Talk to you later.